Welcome to the Faculty Forum Online, where alumni interact with MIT faculty around innovative research and timely topics. I'm Judy Cole. I'm the Executive Vice President and CEO of the MIT Alumni Association, and I will serve as the moderator. To participate, input a username and your location, and type your question at the bottom of your screen. We will do our best to answer as many questions as possible during this half-hour webcast. Today's guest is Dan Cziczo, an atmospheric scientist interested in the interrelationship of particulate matter and cloud formation. Professor Cziczo, thank you for joining us. To start, could you provide our alumni with some context for this program by giving us a brief overview of your work?
Absolutely. Well, I wanted to start by saying thank you, Judy, for having me. It's always a pleasure to come and talk about our research. So as you mentioned, our research group is focused on understanding the emission of particulate matter to the atmosphere and how that leads to cloud formation. So the reason that we're interested in this, as the viewers probably know, is that climate change is an ongoing problem for us right now. It's mainly due to human activities emitting carbon dioxide and other greenhouse gases to the atmosphere. So we know that these are coming from fossil fuels. We understand what's happening rather well. So these greenhouse gases are emitted to the atmosphere. They trap some of the heat that the Earth is trying to give off, and they raise the temperature of the planet. So a quick analogy would be it's a bit like laying on the couch and being perfectly fine in temperature, and somebody comes by and throws blankets on top of you, and you warm up. So what we're focused on is understanding particulate matter. And particulate matter it's much less well understood when it comes to climate change. So just as human activities are adding greenhouse gases to the Earth system, they're also adding particles. And those particles can do two things. One thing is that they can scatter some radiation back into space. So this is the solar energy, the sun's rays, which are coming into the planet. And some fraction of those are scattered back into space by particles. Particles can also form clouds, and as anybody flying around in an aircraft knows, when you fly over the top, these are very white, so they're very reflective. It's like walking out on a partly cloudy day. When you're under the cloud, the temperature is a lot lower. You don't feel the sun's energy hitting you, and this is the same for the whole Earth system. So although we know greenhouse gas emissions and their effect rather well, human activities are also putting out particles. We're also changing clouds, but we don't understand those effects quite as well. So if we go a little further in our analogy, where you're laying on the couch perhaps and somebody throws a blanket on top of you, imagine going outside, you're sitting at the beach on a nice sunny day, somebody throws the blankets on top of you, you get warmer, and now somebody comes by and they put a couple sunshades around you and they block out some of the sun. So you might think that those two things balance each other out, but we don't really know the effect of aerosols and clouds, so some of that sunlight's still getting through, so maybe you're warming up, but not quite as fast as you would otherwise be warming up if those sunshades weren't there. So to understand this, we use sort of a combination of field studies and laboratory studies. The field is great. We use a lot of research aircraft. We'll go out and we'll sample clouds in their natural environment. We'll sample particles where they're being emitted, as well as in the free troposphere and in the atmosphere in general. And doing this, we can find our way into those clouds. We can figure out what the particles are in the atmosphere, and we can figure out what subset of those particles form the clouds. And to do this, we've developed a number of different instruments. So this is one I was told that I could do show and tell today, so I thought I'd bring some of our toys along.
Absolutely.
So this is one of the inlets that we've developed, and this is actually an inlet that's capable of bringing in particles as well as the cloud, the droplets, and the ice crystals in those clouds. And then we can separate out the particles that didn't form the cloud and keep only the droplets or only the ice crystals behind. And then we can run these into our other instruments and analyze them. So we use techniques like mass spectrometry to figure out the chemical composition of the particles. We can figure out their optical properties as well. We can bring them back to the laboratory. We can bring them to the electron microscope facility at MIT and understand their surface properties, very, very specific properties of those particles. And although we like doing field studies, they're fantastic for figuring out what particles are actually in the environment. Clouds have sort of a mind of their own. They form where they want to form. So if we really want to understand the actual conditions, the temperature and the relative humidity at which they form, we have to do that in the laboratory. So we've developed a set of cloud chambers where we essentially have tunable knobs. We can set the temperature, we can set the relative humidity, and make an artificial cloud.
How big are these?
Normally, these are things that we still like to be able to bring into the field and sample particles. So they might be, on the order of a couple of meters, 6 feet tall, or something like that. We tend to try to put them on wheels so we can move them around and take them with us or take them to other laboratories. So we use this combination. We go into the field and we figure out what the particles are that are important, and then we have the ability in the lab to look at cloud formation with very specific conditions. And this is great because it allows us to figure out the exact activation conditions, this temperature and relative humidity at which clouds are forming. So in the atmosphere, we know what the important particles are. One of them is mineral dust. And so I've brought again some toys to talk about. So this is mineral dust that we collaborate with our colleagues in geology and sedimentology. This is mineral dust from the southwestern United States. So we see this in clouds time after time, but we don't really know what the activation conditions are. We bring this into the lab and we can figure it out. And you might think that this is a natural particle in the atmosphere and it wouldn't have anything to do with human activities, but that's not really true, because as we change land usage, as we increase the amount of places that we're putting crops in and changing, cutting down forests and putting in cropland, we're actually putting more and more of this mineral dust into the atmosphere. And in fact, there's some estimates that maybe half of the mineral dust in the atmosphere is there because of human activities.
Wow.
And we also do look at some natural components as well that we're very interested in. And one of the things that we're very interested in are periodic eruptions, volcanic eruptions. So I brought today, this is a bit of mineral dust from the Icelandic volcano that snarled all the air traffic in Europe a couple years ago. So this is actual mineral dust from that volcano, and we're actually able to take that mineral dust and we can grind this up and we can put this into our cloud chamber and figure out when it forms clouds and when it doesn't.
Wow, that's very granular.
It is, yeah.
I expected it to be finer, more powdery.
So it's an interesting question. It turns out that the very largest, the really granular stuff falls very close to the volcano, and that's where this was collected, only within some miles of the volcano. If you go further and further downwind, actually into Europe itself, you find the very finest material. So we actually have size fractions. I brought a rather coarse one today, but we actually have size fractions collected from a number of locations that we sampled.
Interesting. Terrific. Well, thank you very much.
Absolutely.
That was a great explanation. So we will be taking questions from our viewers in a few minutes, but while we wait for them to come in, let me start with one or two of my own. With such a vast research area as the atmosphere, how do you go about gathering research from the field, putting it in a lab context, and then developing workable models? I mean, that's sort of the follow-on to what you were just talking about.
Absolutely. No, it's a fantastic question. I mean, ultimately, we collect a lot of data in the field as well as in the laboratory, and our ultimate goal is to get it into models. We want to understand the Earth's climate system, not only in the present day, but in the past and into the future. And to do that, we have to use these global climate models to do that. So there's a couple of challenges. One is, how much information can we get into these climate models where there's still the computational power to sort of address that information? And that's a challenge for us. The question really is, what's the most important information that we find? What's the most important information for understanding climate? And I can give you an example when it comes to clouds. So in the past decades, the first versions of climate models couldn't carry that much information. They didn't have a lot of computational power. So you could only put in, for example, parameterizing cloud formation with respect to temperature. You would say what temperature it was, and then the model would predict if there were clouds or not forming there. As models became more and more computationally efficient and they had more computational power, we could put more information in. So the next thing that went in was the size of the particles. So we would take the size of these particles, put that into the model, and we were getting better results. And that's been in place now for a few years. So what we're working on now is putting in the chemical composition of the particle. So you can imagine something like this mineral dust that I showed you for a given size is going to form clouds very differently than, say, a sea salt aerosol that's exactly the same size. So that's what we're doing in the present day. If I had to guess, in the future, we might even be able to put in something like the surface character of the particles. We might be able to say how long that particle was in the atmosphere, how much it had aged, how much it had interacted with other particles, and how that might lead to its cloud formation potential or its optical properties for some of these effects that I talked about.
Does the relative humidity affect the creation of particulate clouds as well? I mean, when I think of clouds, I think of moisture. And you're talking about parameters that are not moisture. So how does that interact with it as well?
Yeah, it's a great question. I mean, one thing, taking sort of a step back that I probably should have mentioned earlier on, is that, you know, we now know that at the heart of every cloud, droplet, or ice crystal, there's one of these aerosol particles. They act as sort of the nucleus. They're sort of the seed on which that cloud forms. So you have to have this combination of both things, the particulate matter, the seed particle that's there, as well as the presence of water vapor.
So that's why you always get a residue after a rainstorm.
Exactly.
Oh, fascinating. I love that. All right, I should start taking questions from our viewers instead of just monopolizing it. Have particles, this is from Melinda in Cambridge, have particles and clouds increased over North America and Europe following the buildup of manufacturing since the Second World War?
Well, thanks for the question. It's actually a fantastic one. So, so that's actually one of the interesting things that has happened. I talked about greenhouse gas emissions to the atmosphere, and that's been happening since the Industrial Revolution took place. And we know that it's been increasing as time goes on. Particles are harder to understand because they have very sort of local or regional scales to them. So, for example, since the Second World War, we know that there's been a lot more manufacturing going on in places like the upper Midwest, the Ohio River Valley, and in the United States in particular. So those sort of ramped up after the Second World War. They might have reached a peak in the 60s or 70s. There was a lot of particulates being put out. And the climate in those regions was probably a little bit cooler because of this addition of a sort of a sunshade in those locations. That's actually tapered off and gone away. So as emission controls have come into place, a lot of those particles have been taken out of the system. But they've sort of popped up in other locations. So you can think of the developing countries in Asia, China and India and some of these places, where they're putting out a lot of particulate matter right now. And that's probably leading to changes in their sort of radiative budget and their local climate. There's actually, speaking of after the Second World War, there's one really interesting case, which was the former Soviet Union. They burned a lot of very dirty coal that had a lot of sulfur in it and put off a lot of particulate matter. There was a great deal of industry in the former Eastern European bloc area. And the Soviet Union is an interesting case because the economy sort of stopped when the bloc was broken up in the late 1980s and early 1990s. And this happened, you know, almost overnight. Within a year, a lot of that industry had stopped producing. And there's actually been observed an increase in temperature in those areas as you took the particles away at the same time. You sort of took away their sunshade, and all of a sudden the temperature went up. So it's this sort of fascinating sort of experiment that was performed unintentionally in that region.
Well, it's wonderful that you're there to capture the information and analyze it. PH in Westchester County asks, for those of us who last studied earth science in junior high school, can you recommend any single definitive work on climate change and humans' role in it, especially in the context of the policy debate in recent years?
Oh. Yeah, that's actually it's a very, very good question. This idea of climate change, a simplified form of it. The one that I would most recommend is there's this Intergovernmental Panel on Climate Change that came out in 2007. So this was the very famous one that won the Nobel Prize along with Al Gore. And some of those folks, a lot of those folks actually work at MIT that worked on this report. There's actually a new one that's due out in 2013. And one of the fascinating things about that report is that it comes with a summary sort of for policymakers at the very beginning. So there's a set of 4 or 5 pages at the very beginning of that report that are breaking down the science into the more basic terms, the things that somebody that has taken science but maybe not been a climate scientist for the last 10 or 15 years, it takes it into those terms and just sort of highlights the major findings.
Excellent. That's very helpful. Sandy in Illinois asks, are you saying that because we don't fully understand the cause and/or the effect of particulates on the atmosphere, it may be too early to say that human activity is causing climate change? In other words, is there a chance that human deposition of particulates might cancel out the effect of greenhouse gases?
Oh, that's actually a fascinating question. And this is actually one of the things that's tackled in things like the Intergovernmental Panel on Climate Change report. So my very, very quick analogy of saying that, it's a bit like sitting out on the beach and you're sitting in your beach chair and somebody starts throwing blankets over you and setting up sunshades around you is a bit too simplistic. So we do understand the effect of greenhouse gases much better than we understand the effects of particles and particles on clouds. What we do know with high certainty is that effect, the greenhouse effect. So we know that that's going to lead to a warming, and about how much of a warming. Particles are negative, they're a cooling. They're much more uncertain, but they don't cancel out the warming of the greenhouse gases. So it's a bit like more blankets were thrown on you than sunshades that were put up.
Yeah.
The sunshades are a bit more uncertain in this case, but you're still going to heat up, maybe just not as much as you otherwise would have. So again, just to sort of reiterate that point, because I think it's very important to understand, we understand the greenhouse gases very well. We don't understand the particles and clouds very well. But even with that uncertainty, we still know that it's not enough to offset all of the global warming, all of the climate change that's due to these.
Putting more particles in the air would not solve the greenhouse gas problem.
So that's actually a very interesting question, and it's one of the things that we're working on right now. So some people have suggested this idea of, well, if it's cooling, maybe we should just do more of that, put more particles out. And there's a couple of pitfalls in that area. So one of the important ones is that it doesn't take into account some of the problems that particles bring to the table. And one of them is health effects. So when we think of emitting particles near the surface, of course, that means that you and I are breathing them and everybody's breathing them. And we know that particles cause respiratory problems. It causes childhood asthma. And then there's some very good case studies from the past. I was talking about coal that emits a lot of sulfur particles. This was done, these dirtier coals were burned a lot after the Second World War. And there were some incidents of smogs forming in the United Kingdom. And there were thousands, if not tens of thousands of people that died because of these emissions in specific smog events that can be correlated with particles.
Yeah.
So just simply putting more particles out brings some problems to the table, as well as maybe offsetting some of this radiation.
And I have to imagine that their chemical composition makes a difference too, and what kind of corrosive effect are they going to have on other things that are on the ground if you put more particles into the air?
It absolutely does. Yeah, and this is exactly what was done in the 1970s and maybe early 1980s with acid rain, where a lot of sulfur was being emitted, finding its way into particles, and then you ended up seeing things like, statues losing their faces, acidification of lakes, the large fish kills that went on in the Northeast.
Yeah. So, Ed, in New Jersey, what did you learn about the contribution of particulates from aircraft when traffic was suspended after 9/11? Sort of like the abrupt cutoff of manufacturing in Eastern Europe. Here was another example.
Yeah, actually, it's a very good question, Ed. So there were a few papers that were written after after 2001 on the air traffic halting, and they came in with very mixed results. So the idea was that you stopped for a period of time producing contrails, and contrails are a sort of artificial cloud, and it was apparent that the temperature seemed to rise after that period in time. So this is suspension of air traffic for a few days. Unfortunately, I think that those papers have been viewed a little bit skeptically because you can't take out the effect of large-scale meteorology. So there happened to be a cold front coming into the United States at almost the exact time, and it's proven really difficult to sort of decouple a few days of no aircraft emissions from the large-scale meteorology, cold fronts and warm fronts and things like that. So I would say that the jury's still out on that. I think that in general, it's believed that a suspension of a few days is probably not going to have a large impact on particles and clouds, especially when you think about the context of these larger weather systems.
So we'd have to shut down air traffic control for a much longer period of time in order to be able to understand what that effect is. Am I getting that right?
I wouldn't suggest that because I fly a lot and I've got to actually go home for the holidays in about a week, so I hope that doesn't get done.
Just pick a period of time when you're going to be in one place.
Absolutely.
Okay, so Herman in Los Angeles. wants to know, how much more accurate have the climate models become over the years with particulate matter information included? In other words, when did people really start paying attention to this aspect of climate change?
Yeah, it's another great question. So it's really, I think particles and clouds were always in climate models, but they were very roughly parameterized. So there just wasn't a lot of definition given to the models. It was very crude and very uncertain. So we have been increasing our ability to sort of resolve particle and cloud effects. What I can say is that the error bars are shrinking and shrinking as we go in time. So I think back, I mentioned this IPCC report. These are put out every few years. So there was one put out in 2001. The famous one was put out in 2007 that won the Nobel Prize. There's another one due next year. When particles and clouds were put into the 2001 report, there was no value given to it. It was an error bar. It essentially went from no effect to a large negative effect. Which is kind of funny because I've always thought, if I could do research and actually not give people an answer but only give an error bar, that'd be great. But what we saw in the 2007 report was that a value was then given. There was enough confidence to give it a value, and the error bar shrank down. And I think in the 2013 report, what we'll see is a better value, still within that range, and the error bars will continue to shrink down. Now, they're still much, much larger than the greenhouse gas error bars. Those are understood very well, emissions and effect. But the particle ones are getting better. And so, again, I would encourage the viewers to see those IPCC reports and to read the summaries for policymakers. I think they'd find those very interesting. And you can see those figures as the errors get better.
And if you look at the transition over time, certainly. So Tim in Cambridge is asking, what is your opinion on actively manipulating the presence particles as means of fighting climate change? Do we know enough about the science to safely take such measures? If not, do you expect we will in the future?
Yeah, it's a fantastic question. So this goes back to a bit of what we were talking about earlier, which was
right,
sort
putting
of human
more
addition. Yeah, so we talked about acid rain. For our viewers and some of the folks that might not understand this, there is a subset of folks that have come up with this idea that, okay, if particles are offsetting some of the global warming, that if we add more, we can sort of balance out the warming. And so we talked about the health effects and the reasons you might want to do that. So folks have also said, well, maybe we should add these particles higher in the atmosphere. And one of the ideas is to mimic a volcanic eruption. So after things like the eruption of Mount Pinatubo in the 1980s and even some of the earlier eruptions, we actually saw global temperature dip for a period of a year or two while those particles were in the atmosphere. So it's perhaps not crazy to think that, okay, we could extrapolate this and we could maybe do this intentionally and offset some of this global warming. In my opinion, this is a very, very bad idea, and I'll give you a couple of reasons why I think that. The first thing is that we've spent our time together talking about how uncertain particles and their effect on clouds are. So to imagine that we could somehow find a knob that we could very accurately tune to set exactly the climatic effect that we want, exactly balancing out either some fraction or all of global warming, I think is incorrect. We just simply don't have that ability. We don't have that knowledge now, which is why I'm interested in this area, is improving our ability to do that, increasing or decreasing our error bars, increasing our certainty in the effect. But we don't have that yet. The other thing is that there's a lot of side effects. So we talked about the side effect of particles and health response. There's other side effects. So after a volcanic eruption, we see ozone go down. We see a depletion in the ozone layer. And that's obviously a very bad thing. It's blocking out ultraviolet radiation, and this leads to increased skin cancer, something that we saw in the 80s when the ozone hole was prevalent over the South Pole. So you're sort of locking into a proposed solution for climate change that perhaps has other side effects that are as bad or worse than the initial problem. So you're sort of locking yourself into those things. I mentioned ozone. There's other things like changes in precipitation, making it rain in places it didn't used to, or creating droughts in places that used to have rain. And so I think that these, at least for me personally, are non-starters. If you're proposing a solution to a problem that has such catastrophic side effects, I think that this indicates that we should tackle the problem itself. We know what the issue is, the addition of these greenhouse gases. Simply trying to remove those, lessen their effect, is something that we know what the effect that's going to have. Whereas if we start to try to manipulate particles to offset we bring up this whole host of secondary problems.
And talking about causing it to rain in places where it didn't previously, or to be a drought, also leads to the next comment from Elliot in Augusta, Georgia. Can you comment on smoke from forest fires, like the large ones in Siberia? Have you characterized many of those particulates? And I'm thinking also in the American Southwest, in California and Colorado this year, we've seen a lot more forest fires. And how does that affect all of your study?
Yeah, so forest fires are actually a very interesting problem. One of the interesting things about forest fires is that their area, how much land is being burned by forest fires, appears to be increasing. And that appears to correlate with the increase in temperature due to global warming. So you have more and more fires as the temperature gets warmer and warmer. And this is, perhaps a little bit obvious in retrospect. As you warm, you sort of dry these places out, and it can lead to more fires. So you get this feedback where it gets drier and you start putting more and more particulate matter in. We have characterized those particles. We've done a set of aircraft flights where we sample that material. We understand what it is. Understanding its exact optical properties, how much radiation, how much solar energy is being scattered into space versus absorbed by those fires. Because anybody that's seen those fires knows that they tend to be very dark, very black, as opposed to clouds, which are very white and very scattering. So they may actually reinforce climate change to some extent by absorbing solar radiation and increasing the heating in the atmosphere. And this is something that we're actually working on in the atmospheric chemistry and atmospheric sciences right now.
Fascinating. Alex from MIT Sloan says, I read a recent paper that says that increasing CO2 in the atmosphere leads to less cumulus cloud formation, which leads to less reflection warming of the planet. This seems like a vicious negative feedback loop. Does methane have a similar effect on clouds?
So I think that my answer to that question is I think that this thought that increased greenhouse gas emission to the atmosphere, increased CO2, leads to a change in clouds, and that this could be a feedback cycle. That's actually something that's being looked at right now. So I don't think I would place a high certainty on it quite yet. That's not to say that it may not be true or that there may not be a correlation.
Just hasn't been proven.
I think that we still need to go a bit further in that. It's very hard to decouple, for example, the increase in greenhouse gases from changes in particulate matter in the same way. So to really do that experiment, I think we're going to need some years moving forward to really figure out if that change is actually true and if it's happening or not.
And does methane have the same sort of effect?
If that is true, methane would have the same greenhouse gas warming. It's actually a more efficient greenhouse gas, or something that traps more radiation. So it would be assumed to have the same type of effect as CO2. But again, it's very uncertain if that's direct cause and effect, or if there's other factors at play.
Right. Okay, I think we have just time for one more question. Christoph in Germany asks, what is the biggest obstacle towards progress to achieve global action against global warming?
Oh, boy, that's a very, very good question.
That's a big question.
It's a good one to end with, right?
Yeah.
I think that most of the viewers are probably aware of the Kyoto Protocol, which is going to be ending here in the space of a few years, which was signed on by many nations, but unfortunately not by the United States. And it also had exemptions for the developing nations. The two that are most often pointed out are China and India, which have become two of the top 5 carbon dioxide greenhouse gas emitters. So I guess my answer to that question would be that, as a follow-on to something like Kyoto, it would be very nice to not only get everybody to buy in, but also have some way of addressing the concerns of developing nations, which of course want to develop. They want to have the standard of living of the developed nations, but also sort of phase in reductions in greenhouse gas emissions. I am certainly not a policymaker, and at times like this, I'm very glad to not be, because this is a very difficult question to answer. Yeah. But I think those are the two things. You have to have buy-in by the developed countries, all of them, not just some of them. And you also have to find a way of sort of phasing in the effect, the response by the developing countries as well.
Well, thank you very much. On behalf of the MIT Alumni Association, we are grateful for your insights today, Dan. And thanks to our viewing audience for joining us today. We encourage you to continue discussing this topic on our blog, The Slice of MIT, by following the link that will appear on your screen momentarily, if it's not already there. This webcast is the second Faculty Forum online webcast of this season. We look forward to your participation in this year's series of chats with MIT faculty and researchers. Thank you and have a good day.